So good evening, everyone. Welcome to this extra live session for the course Concrete Technology offered by NPTEL. I am Archit Agrawal, a PMRF scholar from the Department of Civil Engineering, and I will be conducting weekly live session for the entire course duration. So this is an extra session in which I will be covering the leftover part of week 11 and some extra content. And on the coming Friday, we will be having discussion of the week 12 content. So in today's session, we will first revisit the last live session that was for week 11 content, a quick recap, and then we'll look over the leftover things that were covered in the week 11 content. Okay, so the content that we'll discuss today will continue our discussion on corrosion and reinforced concrete. So for this, the session is divided into following sections. First, we'll talk about kinetics of corrosion. Then we'll talk about corrosion control techniques, and then finally we'll talk about in situ monitoring of corrosion in reinforced concrete. In between, I will have some objective and numerical questions, around 12 questions in total, that will challenge your understanding about the concept. And finally, we'll conclude the discussion and I will try to address any other queries post discussion. So, in the last session, we started discussing about corrosion. We defined corrosion in a three-part definition, connecting the cause of corrosion based on thermodynamics, the rate of corrosion based on kinetics, and the effect of corrosion in terms of degradation. Then we looked into corrosion from a cradle to grave analysis point of view framework, understanding it from ion ingress through concrete cover, initiation, propagation, and acceleration, and how the repair against corrosion can be costly as we delay the action against it. In terms of depassivation of steel reinforcement, we talked about direct and indirect effect. Direct effect means when aggressive ion directly affects the steel and not concrete, which is the case of chloride induced corrosion. And indirect effect means when aggressive ion affect the concrete and then the effect of on concrete causes depassivation of steel, which is the case of carbonation induced corrosion. We discussed in detail about carbonation corrosion, what is carbonation, how it causes corrosion, what type of corrosion occurs due to carbonation, how carbonation is detected, and how the carbonation depth is modeled in concrete based on square root of time law. We discussed about chloride induced corrosion. What are the sources of chloride ions for ingress through concrete cover? We discussed how chloride ions move through concrete cover, the initiation phase, how it is detected by different parameters like surface chloride concentration, cover depth, critical chloride threshold, and diffusion coefficient, and what happens after initiation. So, for chloride ion diffusion coefficient, we saw Fick's second law, which is modeled for non-steady diffusion process, and it can be solved based on certain boundary condition and assumptions for calculating the diffusion coefficient parameter. And we saw the application in, like, for rapid estimation, we saw the RCMT testing also. Then we moved into understanding the science behind corrosion. What is electrochemistry? We have first understood electrode potential by understanding activity that is happening at the steel concrete interface, steel electrolyte interface. We talked about standard electrode potential and saw how Nernst equation can be derived from Gibbs free energy to calculate electrode potential in a electrochemical system. And finally, we talked about application of this electrode potential in developing pore-based diagram for a metal, which helps to predict the stability of a metal on a pH versus potential scale. We saw pore-based diagram for nickel and iron, and then we saw for iron how pore-based diagram defines different stability zone. Okay, so this was all that we covered in the last session. So now the next topic that we'll discuss today is the kinetics of corrosion activity. So the electrochemical parameters we discussed till now, that was electrode potential, talks mostly about the thermodynamics, or we can say the possibility of a corrosion reaction to occur. However, for a system which is corroding, what matters to us is the rate of corrosion that represents the kinetics of corrosion reaction. Okay, so the kinetics of a corrosion reaction is represented in terms of it is represented using Butler-Volmer equation. okay, which says that, which describes the electrical current through electrode potential, depends upon the voltage difference between the electrode. Okay, so this is what Butler-Volmer equation describes, like how the electrical potential in an electrode depends upon the potential difference and the bulk electrolyte. Okay, for a simple non-unimodular redox reaction considering both anodic and cathodic reaction happens at the same electrolyte. Okay, so here we are talking about a piece of metal for which there is an anodic and a cathodic reaction is happening. There is a potential difference that has been developed. Okay, so due to the development of a potential difference on the same metallic surface over which both anodic and cathodic reaction is happening, how we can calculate the current that is flowing, that calculation we can do with the help of Butler-Volmer equation. Okay, so this equation that we'll see in the next slide, it is derived using four key relationships. Okay, first is the Nernst equation that we have already seen. Second is the Arrhenius equation that relates the rate of a reaction with the temperature. Then third is the rate of reaction dependence upon the concentration of the reactants. And fourth is how rate of reaction is related to current density. Okay, so for using these four standard relationships, we get the Butler-Warmer equation derivation finally. Okay, so in the figure you can see how Gibbs free energy depends on the reaction. So for converting a reactant into a product, each reaction requires a certain activation energy. Okay, which here in this figure is represented by delta G naught. Okay, now this right now shows the equilibrium condition, because if I am at this middle position, then I need the same activation energy to go backward or forward. Okay, S- so this distance is equal, okay, for forward and backward reaction. So this represents equilibrium condition, that is equal chance of occurrence for both the conversion. Okay, now if we consider a simple electrochemical reaction where a reactant which is in oxidized form is converting into a product which is a reduced form, then at equilibrium both forward and backward reaction has the same affinity. So when we combine all these four relationships, like rate we are writing in terms of current, so I can write as equal to N cross F cross R. Then instead of rate of reaction, I will substitute K cross C concentration. Instead of K, I will substitute the Arrhenius equation factor. And instead of delta G, I will place minus NFE. So when we substitute all the relationships in this equation, we'll get the rate current density for forward reaction is equal to the current density for the backward reaction is equal to NFA e to the power minus NF eta naught upon RT. So this is a general representation how these four equations combine. Okay. Now, if we apply some external potential excitation to the system, so this right now was an equilibrium reaction where both forward and backward reaction has an equal rate. So if I will say here the net current, that is the current for forward reaction minus current for backward reaction at equilibrium, net current which is flowing, that is flowing in the system, will be equal to zero. Okay, however, if we apply some positive potential to this equation, okay, to this reaction, so what is happening when we are applying a positive potential, that means we are consuming electrons. Okay, so this equation will tend to undergo oxidation. Okay, so this is a reduced form, say Fe. This is an oxidized form which is say Fe2 plus. Okay, so when we apply some positive potential, we are consuming the electrons, so we are moving the reaction towards the backward side. So you can remember this as a kind of easy way to remember the side of equilibrium which we consume, the equilibrium moves in that direction. Suppose I am adding more Fe to the system. So what will happen? The equilibrium will move towards backward direction. If my Fe is getting consumed more, then the equilibrium will move towards forward direction. Okay, the same thing with Fe2 plus and electron also. If I'm consuming more Fe2 plus ions, then the equilibrium will move towards forward direction. If I'm consuming more electrons, then the equilibrium will move towards backward direction. Okay, so this is how the equilibrium shifts based on the application of a potential or change of pH also, if we had OH minus ion or H plus ion in the equation. Okay, So when we apply positive potential, the reaction tends to undergo oxidation. So we can see from this shifted free energy versus reaction kinetics plot that now we can see that this equilibrium is closer to the backward reaction while it is far away from the forward reaction. Okay, so we can say for oxidation, now like required delta G is less than delta G naught, which was right here right now. Okay, so you can see this is smaller. Okay, delta Ga is smaller than delta G naught, and delta Gc is now greater than delta G naught. Okay, so we can write delta G is something delta G naught minus alpha NFE, and delta Gc is something delta G naught plus 1 minus alpha NFE. And here this alpha factor, it represents the charge transfer coefficient, which defines the ability of a reaction to undergo oxidation or reduction. So this was originally 1.
तेरा कब होगा उनका ये अरे तेरे चाची चाचे पट्टी देखी चलो चला जाएंगे तो
Okay, so this total is 1. Okay, so this is my backward reaction rate, so I can write it as alpha b. This is my forward reaction rate, which is alpha c, alpha f. So always alpha b plus alpha f is equal to 1. Okay, so if I am representing for backward reaction, I am representing by alpha, then alpha f will be nothing but 1 minus alpha. Okay, so these are known as transfer coefficient. Okay, if my reaction tends to undergo oxidation or it tends to undergo backward, it is more favoring towards backward side, then what will happen, this alpha value, alpha b, will be smaller than zero point 0.5. Okay, initially both are zero point 0.5, zero point 0.5, but if reaction tends to undergo oxidation, that is the backward side, then this transfer coefficient will also reduce. Okay, because reaction is favoring that side. Okay, so now since rate of forward reaction and backward reaction are different, so we will have a net current flowing in the system, which will be nothing but I net is equal to I oxidation minus I reduction. So this is my backward reaction current and this is my forward reaction current. Okay, so knowing this equilibrium relationship that we derived here, if we substitute both I oxidation and I reduction, we'll get the net current flowing in the system. Okay, here this neta that you see, instead of delta E, instead of E, we have written neta, and this neta is known as the over potential that we have applied. So initially we said we applied some positive potential. So that positive potential is nothing but represented by neta, and that is known as over potential. Okay, and this relationship between current density and over potential that incorporates kinetics of both forward and reverse reaction. This relationship is known as Butler-Warmer equation. So you can see this is the net relationship. Okay, and in this relationship, this factor alpha n nf upon rt, this factor we assume as a constant value, 1 upon beta a, and for backward reaction we assume this as 1 upon beta c. Okay, so this beta a and beta c, these are known as Taffel's constant. Okay, Taffel's slope constant. Okay, so you can see how this neta and I are related. Okay, so this is my neta on y-axis and this is logarithmic of the net current on x-axis. So they follow this exponential trend. Okay, and this is when there is we are at equilibrium. When neta is equal to 0, it means there is no extra external potential applied. So at that point we can see that the current is tending towards 0. Okay, so at equilibrium current is 0. At as we apply over potential and more positive over potential, the current increases, and if we apply more negative over potential, the current again increases. Okay, so this is the representation of neta versus log I for Butler-Volmer equation. Now there are two special cases in Butler in this equation. Okay, first case is if we apply very high polarization. So this neta value, that was our over potential, if this is very 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 greater than zero, okay, very large over potential we are applying. So what will happen, this term that you are seeing, the second term, 1 minus of 1 minus alpha n f neta upon rt. Okay, so this term, if neta is very large, okay, in positive direction, then what will happen, this e to the power, this value, it will tend towards e to the power minus infinity, and this will be nothing but equal, it will approach to zero. So my net current will be defined only by this first factor, which is e to the power neta a upon beta a. Okay, so I can write neta a, if I take log on both the side, I can write neta is nothing but beta a 2.303 log I by I naught. Okay, so this is this line, okay, which defines the slope of the anodic curve. Okay, similarly, if neta is very very less than 0, or neta tends to minus infinity, then what will happen, this first term will become equal to 0 and this second term will remain. Okay, so net current will be due to the cathodic reaction. Okay, so I can calculate neta c again from this equation, and this represents the slope of second equation. Okay, so these so we say that why this, we say these are special cases, because when we apply very high polarization either in positive direction or in negative direction, this curve that was originally like this, it tends to become linear. Okay, and the slope of that linear line is defined by beta a and beta c. Okay, and these slopes, they are known as Tafel slope, and this special case, it is known as Tafel's extrapolation. Okay, similarly, if we apply very small polarization potential, so if this neta value is very, it tends to zero, then what will happen, I can write an exponential expansion, this function I can write as a exponential function. Okay, so I have this function e to the power x, where x tends to 0. So using this mathematical relationship of Maclaurin's series expansion function, when x tends to 0, e to the power x can be written, represented by this expansion function. Okay, so we can write this e to the power neta upon beta a, and e to the power minus neta upon beta c, we can expand using this relationship, okay, mathematical expression, and it will come out to be like this. Okay, so in this, all the higher order terms, they will tend to 0 because neta tends to 0. So neta square, neta cube, all these value will be almost equal to 0. So we can ignore them, and we can just write directly this relationship, which when we simplify, it will convert into I is equal to I cot 2.303 neta upon beta a plus neta upon beta c. And this relationship is known as Stern-Gary relationship. Okay, so when we apply very small polarization potential from Butler-Warmer equation, we get the Stern-Gary equation, and we apply very high polarization potential. So from Butler-Warmer equation, we can get the Tafel's extrapolation. Okay, and if we know this value of I, and we know that we have applied a very small neta, then we can use Ohm's law to calculate the resistance also. So we know Ohm's law says that V is equal to IR. So R will be equal to V by I. Okay. So we know the equation of I. So we can get, and we know V is our neta. So we can get polarization resistance also. Okay. This is only true when we apply very small permutation potential. Okay, so these are two special cases of Butler-Volmer equation, for very high polarization and for very small polarization. Okay, now based on these relationships that we have seen, just try to solve this simple numerical. Okay, and in the meantime, if you have any doubt regarding Butler-Volmer equation or any part of the derivation that you are not able to understand, you can ask. If there are no doubts, just try to solve this question. So in this question, you have been given Tafel slope value, and you have been given a potential. okay, that has been applied and you have been given current density. You need to calculate the polarization resistance and you need to estimate the current for an overpotential of 100 millivolt using Butler-Volmer equation. So I will paste both the relationships for you so that you can do the calculation. So for polarization resistance, we have this relationship, and Butler-Volmer equation, you know, this is the relationship. Just give it a try. If you have any doubt regarding any part of the kinetics that we have discussed, you can ask. Okay, the more you will ask, the better clarity you will get. Can anyone tell me the answer for question number part A of this question?
चालू मारते आपण या आज जमाना जमान्याने सगळं केलं की जे जे काम करायचं लकी लागतं मध्ये
Okay, so you just need to substitute these values here that is given in the question. So ICOR is given as zero point 0.5 microampere per centimeter square. So for micro, we will convert microampere into ampere. So that will be a multiplication of 10 to the power of minus 6. Okay, times 2.303 times beta A plus beta C. So it is 0.12 plus 0.10 whole divided by point 0.12 times 0.10. Okay, so when you will substitute and this is 1 by r, so we need to calculate r. Okay, so when you will substitute r value, it will come out to be 47400 ohm centimeter square. Okay, so this is the polarization resistance, okay, for this much amount of current and this much amount of uh, TAFL constant values. Okay, so this was part A, how we calculate the polarization resistance if we know the TAFL slope parameter and the corrosion current density. And second, so part B is we need to calculate net current if we know this much amount of over potential we are applying. So first we'll calculate this beta and beta C value. Okay, so alpha, Okay, so assuming that we are at equilibrium, we will take alpha as zero point 0.5, n is 2, f is 96485, r is 8.314, and t is 298. Okay, so it is given to us alpha a and alpha c is zero point 0.5, t, f, and n is equal to 1, we need to assume. Okay, so this is my beta a. Similarly, since alpha is equal to zero point 0.5, beta and beta c both will be equal. Okay, so from this we can calculate the value of beta a and beta c. Okay, 1 upon beta and 1 upon beta c. Okay, so this will come out to be 1.945. Once we calculate this, we just need to calculate I net. Okay, so how we will calculate I net? So this is 1 upon beta and 1 upon beta c. I net will be nothing but I naught, which is given to us. It is zero point 0.5 into 10 to the power minus 6. Okay, zero point 0.5 into 10 to the power minus 6 into e to the power 1.945. So here we can multiply this over potential also of zero point 0.1. Okay, so it is e to the power 1.945 minus e to the power minus 1.945. Okay, since alpha a and alpha c are equal, so both the terms will be equal. Okay, so at this stage I net, it will be coming out to be 3.24 microampere per centimeter square. Okay, so this is how we apply Butler Warmer equation if we know the different parameters. Okay, I hope this question is clear. Any doubt in this question? So in the first part, we calculated the polarization resistance, knowing the Tafel slope value and the corrosion current density. And in the second point, knowing the overpotential that we have applied, we calculated the current. Okay, so you can see at equilibrium current was zero point 0.5 microampere per centimeter square, which is a very small value. However, when we applied a small over potential of zero point 0.1 volt or 100 millivolt, you can see the currents changed from zero point 0.5 to 3.42 microampere per centimeter square. Okay, so this is what we have seen here also. Okay, so as polarization, as we apply permutation potential, as we apply polarization, there is a sharp increase in current. Okay, across equilibrium. Okay, let's move ahead. Now, the straight line that we got from Taffel's extrapolations, we have seen in the first case here that when we apply very high permutation potential, we get straight lines. Okay, this equation tends to go as a straight line. So these straight lines, they are used to plot what we call as Evans diagram. Okay, so you can see this was my actual Butler-Volmer equation. Okay, which is tending to 0. Okay, and when we apply very high permutation potential, we get this green line. Okay, which is like a tangent to this curve, and these two green lines whose slope we know are is neta a and neta c. These lines are known as these lines are used to make a plot which is known as Evans diagram. So an Evans diagram, it is a pictographical representation that depicts the graphical representation between electrodes kinetic data and thermodynamic potential in a corrosive process. So this is my thermodynamic parameter and this is my kinetic parameter. Okay, so it is a representation of potential versus current. Okay, an Evans diagram is also known as a mixed potential plot. Why? Because mixed potential theory explains metallic corrosion as a reaction of two or more electrode working simultaneously. So this we'll see in next two slides, where we'll talk about how Fe and zinc, if we plot their Evans diagram on the same graph, we'll see how they interact, okay, in the same medium, how different metal interact differently. Okay, so using Evans diagram we can study mixed potential theory also. Mixed potential theory means when there are multiple electrodes that are present simultaneously in a electrolytic system. Okay, for a metal immersed in electrolyte, the Evans diagram is represented by two lines. So one is the anodic line and one is the cathodic line. Okay, so anodic line represents an anodic polarization and the other represents cathodic polarization. Okay, both having slopes known as Tafel scan. So suppose I have iron. So Fe converting into Fe2 plus, this is my anodic reaction. So this will be my Tafel's line for the anodic reaction, which will have a slope of beta A. Then the cathodic reaction will be Fe2 plus converting into Fe. Okay, so for this, my Tafel equation will be Tafel's plot will look like this, and its slope will be beta c. Okay, so this is what, for every metal, this is how Evans plot diagram is plotted. Okay, so it is represented by two lines. This is my anodic polarization line and this is my cathodic polarization line, and this is my equilibrium point where reaction kinetics for both backward and forward reaction are the same. Now, if we see the application of Evans diagram, we see here in terms of iron and zinc corrosion kinetics when they are immersed in an acidic solution. So, here both zinc and iron are immersed in the same acidic medium but separately. Okay, so the blue line in the Evans diagram that you see here, okay, it represents Evans plot for zinc. So this is the anodic reaction for zinc, and this is the cathodic reaction for zinc, as you can see from these equations. Okay, now these orange line, they show the Evans plot for HCl activity at the zinc electrode. So this is my zinc electrode. Okay, here zinc is converting into Zn2 plus, and what is the activity of H plus ion at the surface of this zinc electrode? It is represented by these orange lines. Okay, so it's we have anodic branch here and we have cathodic branch here. So we know metal undergoes oxidation and the electrolytic solution will undergo reduction. So interaction of this line and this line will give me the uh, corrosion potential and corrosion current density for zinc in acidic medium. So you can see it is interacting at this point somewhere. So this will give me the corrosion current density for zinc and corrosion potential for zinc in a acidic medium. Okay. Similarly, for iron, we have this black line. So this is the anodic curve and this is the cathodic curve for iron. Okay, and these light yellow lines represents the HCl activity on the surface of iron electrode. Okay, so this is the anodic branch and this is the cathodic branch. So interaction of this cathodic branch of HCl and anodic branch of iron will give me the corrosion current density for iron and corrosion potential for iron in acidic medium. Okay, so you can see that for zinc, my electrode potential is somewhere uh, close to 0.76 volt. Okay, however, for iron the electrode potential is less negative, it is around minus 0.44. Okay, and the current that is the corrosion current density for iron is greater than the corrosion current density for zinc. So we can say that iron will corrode faster compared to zinc in a acidic medium because it has a higher current density. Okay, I hope this is clear. Okay, now this was when zinc and iron are present in the acidic medium, but they are separate from each other, they are not connected. Okay, however, if we connect zinc and iron together like it is shown here, okay, so now zinc and iron they are connected together sidewise and then we immerse them in an acidic medium. So what will happen, the four lines, okay, that we saw, they remain the same. However, now we will have a net anodic reaction and a net cathodic reaction. So net anodic reaction will be summation of anodic reaction of zinc plus anodic reaction of iron. So it will start from here, okay, and these two equation, this one and this one, it will add. Okay, so net anodic reaction is something like this. Okay, and net cathodic reaction will be summation of this line, the reduction of HCl at zinc electrode and reduction of HCl at iron electrode. So this will be this line. Okay, so the interaction of net cathodic reaction and net anodic reaction will be somewhere this point, which will give me the net current density in this system. Okay, so here if we see the horizontal line, the potential of both iron and zinc, they will be the same. But in this net current I net, if we see what is the contribution of zinc and what is the contribution of iron, so when we draw a horizontal line, so we'll see that it is interacting the anodic curve of zinc at this point and it is interacting the anodic curve of iron at this point. Okay, so we can say that the current contribution, the corrosion current density of zinc is higher than the corrosion current density of iron. However, when they were separate, the current density of iron was greater than current density of zinc. So this is known as galvanization. Okay, so when we connect zinc with iron, what happens? Zinc act as a sacrificial anode. Okay, it sacrifices itself to protect iron, and this thing gives rise to the process of galvanization, where zinc coating is done on steel bars to protect steel from corroding, because zinc has a higher corrosion tendency, so zinc will corrode instead of iron. Okay, so using Evans diagram and the mixed potential theory, we are able to understand how multiple electrodes, if they are present in the same medium, how they respond to the medium, which one will corrode more, which one will corrode less, and how they will perform if they are connected together. Okay, now, once we know the current density, that is I naught, we can determine the rate of corrosion using Faraday's law. Okay, so the amount of any substance that is deposited or liberated during electrolysis is proportional to the quantity of charge passed and equivalent weight of the substance. So this is Faraday's law. So what Faraday's law say, that mass loss of a metal is directly proportional to charge passed, and mass loss is directly proportional to the equivalent weight of the metal. Okay, so removing this proportionality signs, we get that mass loss is equal to 1 upon f times q into am upon n. So am is the equivalent weight of the metal. For fe, we know it will be something around 56. N is the valency, the charge transfer. Okay, so we are converting fe2 plus into fe, so n will be equal to 2. Q is the amount of charge passed. Okay, and f is the Faraday's constant, that is 96485 coulomb. Okay, so this is Faraday's relationship. Okay, now since we know that corrosion is a surface phenomena, so when we talk about a metallic corrosion, corrosion starts from the surface. Okay, it happens at the interface of electrolyte and metal. So you can say that corrosion rate is nothing but mass loss per unit area per unit time. Okay, so mass loss, we know it is represented by this. Instead of q, we can write charge part is equal to total current passed into time. Okay, so time and time, it will cancel out. I, capital I, total current passed upon total area will give me the current density I naught. Okay, so my final equation will come out like this. So corrosion rate is related to I naught by this equation, and this is when this is for uniform corrosion. So when uniformly corrosion is happening throughout the surface. However, in cases of pitting corrosion like chloride corrosion, instead of representing corrosion rate by mass loss per unit area per unit time, we represent corrosion rate by mass loss per unit area per unit time per unit density of the material. Okay, so there is an additional density factor that comes into picture for localized corrosion. Okay, so this equation was for uniform corrosion and the second equation is for localized corrosion. Okay, the unit for uniform corrosion is nothing but gram per meter square, and for localized corrosion it is generally millimeter per year or milli inches per year. Okay, so this Faraday's law helps us to relate current with corrosion rate and current. Okay, now try to answer this question. So here I have given you Taffel's constant value, okay, and I have asked you to calculate me the Stern Gary constant B. I asked you to calculate the corrosion current density. You know the polarization resistance also, and then the corrosion rate. Okay, so just try to attempt this question, and in the meantime, if you have any doubt regarding Evans diagram, zinc and iron interaction, and Faraday's law, you can ask. So I'll just paste the numerical relationships for you so that you can calculate. So this is one relationship and second relationship is given to you in the question. So using these two relationships, you need to answer all three parts. Just give this a try. So you know the polarization resistance and you know the Taffel's constant. Okay, so you need to give me Stern Gary constant. Stern Gary constant is this. Okay, 1 upon beta a plus 1 upon beta c. This is generally presented by a single term which is known as b. Okay, and this b is known as Stern Gary constant. Look at this entire thing, 2.303 times 1 upon beta a plus 1 upon beta c is the Stern Gary constant. This is 1 by b. Okay, and Stern Gary constant is b. So have we calculated what will be the Stern Gary constant value? Can anyone tell me? So when you will substitute beta and beta c values, I have substituted them in terms of volt per decade, okay, instead of millivolt. So when you substitute this value, solve the relationship and take the inverse, you will get B value as 23.7 millivolt. Okay, so this is my Stern Gary constant. Okay, so this is the solution for first part. Okay, so this type of numerical they can come in the NPTEL exam also. For this you need to remember the Stern Gary relationship. If you know this relationship, answering part A and part B of this question will be very simple. Okay, so this is the value of beta. Then if I want to calculate current density, so that is nothing but 1 upon r is nothing but I core, and this is that we have calculated as b. Okay, 1 upon b. Okay, so I core, it will be nothing but b value, that is 23.7, divided by polarization resistance, that is 1000. So that will come out to be 23.7 millivolt. Okay, so this was in volt. That will come out to 23.7 micro ampere per centimeter square. Okay, so this was in millivolt. So millivolt, if I will divide by 1000, it will convert into microvolt, and volt upon ohm will convert into ampere. Okay, so that's a 23.7 microampere per centimeter square. So this is my current density. And corrosion rate you can then calculate simply by substituting the current density value in this relationship. Okay, so it will be nothing but 0.00327 times 23.7 times E naught, that is 56, divided by rho. So density is 7.87. Equivalent weight. So equivalent weight is molecular weight divided by charge density. So that is 56 divided by 2. So it is 27.92 exact value. Okay. So when you will substitute all the relationships, so this will come out to be 0.275 mmPy. Okay, so this is the rate at which corrosion is occurring on the steel surface for this much polarization resistance and this much current density. Okay, so in this way we have seen combination of Stern-Gary relationship and corrosion rate estimation. Okay, so the Stern-Gary relationship helps us to calculate the corrosion current density, and then using Faraday's law solution we calculated corrosion rate from current density. Okay. So there is one more similar question that I will advise you to try on your own. So again, I have given you TAFL extrapolation factor beta A and beta C value. I have given you the over potential value, and I have given you the current density, and you need to calculate the corrosion rate. So you know the relationship. Just give it a try. Okay. So the answer I will just tell you, it will come out to be 0.0116 mmPy. Okay, so just give it a try. You know all the point data required for the calculation. You need to calculate the corrosion rate. Okay, so if you are not able to get the answer, you can discuss with me in the next class. Okay. Any doubt in the kinetics of corrosion part? Anything that you were not able to understand? Anyone? Okay, if there are no doubts, we'll move ahead. So, so for now, if we just summarize the electrochemistry part of corrosion that we have discussed, so there are four steps that are present in a corrosion reaction. Okay, the anodic reaction, half cell. Okay, so here iron is converting into iron 2 plus. Okay, then there is transport of electron within the metal surface. So if we see, this is my steel reinforcement. At this side, Fe is converting into Fe2 plus. Okay, leaving behind electrons. Okay, these electrons, they move inside the steel. Okay. Okay, so movement of electron from anode where they are produced to cathode, where they will be consumed, it happens. So this is my anodic side and this is my cathodic side. So here electrons came. Okay, and then we have cathodic reaction where oxygen in the presence of moisture, it will consume these electrons and it will make OH minus ions. Okay. Now these ions that are formed in the electrolytic solution, so these ions, they will move through concrete pore solution in the presence of water and in the presence of chloride ions. So the transport of ions will occur. Okay, so from here to here ions will move and it will combine, both these ions, they will combine to form rust. Okay, so what we can see, there are four steps. There is anodic reaction half cell, there is cathodic reaction half cell, there is movement of electron within the metal, and then there is transport of ion through concrete or any other electrolytic solution outside metal. Okay, now the ones that are highlighted in red in this cell are the ones which can be controlled. Like we can slow down the rate of either anodic reaction or cathodic reaction or both, which will slow down the net corrosion reaction, or we can slow down the movement of ions through concrete, which can slow down the corrosion reaction. However, we can never slow down the electron movement inside reinforcement because metal is a conductor. Okay, so electron will flow, we can't slow down the electron movement. So probable areas where we can control corrosion or we can mitigate corrosion can be either controlling the anodic reaction or controlling the cathodic reaction rate, or controlling the or slowing down the movement of ions through concrete cover. Okay, so on a broader scale, there are three ways to deal with corrosion. Okay, first is the cathodic reaction control method, which is to lower down the rate of cathodic reaction, and this includes proper designing and detailing of cover concrete or coating the concrete surface. Okay, then there is anodic reaction control method, which slows down the rate of anodic reaction, that is Fe converting into Fe2 plus. Okay, so this includes electrochemical techniques like impressed current cathodic protection or sacrificial anode cathodic protection. It includes corrosion inhibitors, okay, which are applied, which forms a coating over the steel surface. Okay, and there are coated reinforcement, epoxy coated bar, cement coated bars, and all those things. And in electrochemical technique, an electrochemical technique, we have sacrificial anode cathodic protection, just like we saw here, galvanization. So this is also kind of sacrificial anode protection. So what happens when we galvanize a steel, when we connect a steel rebar with a zinc bar, so what will happen, instead of iron, zinc will corrode because it has a higher corrosion tendency when it is connected to iron. So iron is getting protected and zinc is getting corroded. So this is known as sacrificial anode cathodic protection. Okay, so that is also one type of electrochemical technique which can reduce the rate of anodic reaction. Then there are metallurgical control method where we make use of special reinforcements like stainless steel, which have a strong passivation tendency, which delay the occurrence of corrosion. Okay, so these are different ways in which we can deal with corrosion. Now, among these different ways, if we focus on the role of concrete, so this diagram uh, tells us about corrosion stages that we saw earlier. So we saw there is initiation period, ionic diffusion happens through concrete, while in the propagation period, there's ionic diffusion also happening and there is concrete cracking also happening. Okay, so there were four parameters that were associated there. There are four parameters that are associated with concrete that can affect both initiation and propagation phase. First is the porosity, second is permeability, third is concrete cover, and fourth is near surface property. So porosity, so permeability or pore interconnectivity or cover quality, they can affect the initiation period. Okay, they can determine how quickly a corrosive ion reaches the steel surface. Okay, so based on the permeability of my cover concrete, the amount of interconnected pores that are present in the cover concrete, and the quality of my cover concrete, I can delay the initiation, I can slow down the ingress of chloride ions, okay, which can delay the corrosion initiation. And second, based on the moisture availability, the oxygen excess, and the ionic conductivity, these factors of my cover concrete, they can control the rate of corrosion or cracking in cover concrete, or they can control the propagation period. Okay, now how they affect corrosion? So permeability defines the ability of concrete to allow fluids to pass through its pore structure. So if I have higher permeability in concrete, ions can penetrate easily, so corrosion initiation will happen fast. However, if I have low permeability, then there is greater resistance for ion ingress, so it will delay the corrosion. Okay, now what all factors of concrete quality they affect permeability? So water to cement ratio or curing or use of mineral admixture can affect the permeability. So if I have a dense concrete or if I have a higher strength concrete, then the amount of pores inside concrete will be lower. So it will have lower permeability also eventually. Okay. Then second is the interconnected porosity. So interconnected pores are the creates the pathway for ionic movement to happen through concrete. So it is not like if there are isolated pores present in the concrete cover, they won't affect the ionic ingress, but it is the interconnectivity of pores through which ions they move from the top of the cover to the steel reinforcement surface. So the amount of interconnected pores present inside the concrete, they can significantly influence the rate at which the period of corrosion initiation and propagation. So if we have a higher interconnectivity in pores, the diffusion of ions will be faster, so corrosion will initiate earlier and there will be higher corrosion rate also during propagation. Okay, so what all factors which affects the concrete pore connectivity? Again, W by C ratio, corrosion curing period, and use of mineral admixture. So if we have a dense concrete or if we have a high strength concrete, it will have low porosity. If the porosity is low, permeability and pore connectivity will also decrease. Okay, then cover concrete quality. Okay, so the concrete cover, it is the first line of defense against ionic ingress. So its quality and depth will directly influence the rate of steel corrosion. So if we have a poor concrete cover, like if we have honeycombing or cracking or very low cover depth, then it will offer low resistance to ionic ingress. So initiation and propagation, it will happen faster. However, if you have a dense, well compacted and high thickness cover, so it will delay both initiation and it will slow down the propagation also. So compaction, curing, and resistance against segregation and bleeding, they play a very important role in defining the quality of cover concrete, which will play a very important role in resisting in delaying corrosion from happening. Now, often we apply coating on concrete surface which act as an initial barrier against ingress of aggressive ion. Okay, so these two images show an example of how coating delays CO2 ingress. Okay, so the image on the left is of a concrete which was coated by an anti-carbonation paint. Okay, while the image on the right is a concrete which was not coated without, which was not coated, okay, with any paint. Okay, so both the concrete, they were kept in an accelerated carbonation chamber, okay, for 15 days at a certain CO2 pressure. Okay, now after 15 days, what we did, this was our sample. We splitted the sample from between and we sprayed phenolphthalein indicator on the cross section. Okay, so we know phenolphthalein indicator, it gives us an estimation of the how much is the carbonation depth. Okay, so you can see there is a clear difference in the concrete which was coated on the surface by anti-carbonation paint. You can see the carbonation depth is almost zero. It is like close to zero point 0.5 mm. Okay, very close to the surface carbonation happened. However, for an uncoated concrete which was not coated by any paint on the surface, there is higher degree of carbonation depth. Okay, so CO2 was able to penetrate much deeper. Okay, so within 15 days it was able to penetrate up to 9 mm. Okay, so this is the effect of coating. This is the role of coating in corrosion mitigation. Then instead of applying the coating on concrete, if we use coated reinforcement, okay, we can use coated reinforcement also. And commercially available coated reinforcement in India are if epoxy coated bar, cement polymer composite coated bar, and dual zinc galvanized epoxy coated bar. So these green color that you see on the top of the reinforcement, this is epoxy coating. So how it is applied? We initially heat the steel rebar up to a temperature of 200 degrees Celsius, and then we pass this heated rebar through an electrolytic spray which contains fine epoxy powder. So when we pass this rebar at high temperature through this this spray of epoxy powder, the epoxy, it fuses on the surface of reinforcement, and it forms a physical barrier over the reinforcement surface. So now oxygen or moisture, it can't directly interact with the steel, because now there is a physical insulating barrier of epoxy which is present on the steel surface. Similarly, we have cement polymer composite coated rebar. So in these, how this rebar is made, so we have normal steel. Okay, it is coated with a primer coat of a thermoplastic resin, and then over that resin coat we apply a cement slurry coat. Okay, so we get a cement polymer composite coated rebar, which again act as a physical barrier between moisture and oxygen and steel surface. Then this third, one more type of coated rebar that are present in Indian markets, and these are dual zinc galvanized coated rebar. So first, the steel rebars are galvanized with zinc. So on the steel surface, we do a thin coating of zinc. Okay, so we have seen galvanization earlier also. Galvanization, zinc will corrode instead of iron. Okay, so zinc will act as a sacrificial metal, and on the top of this galvanization, we cover a thin layer of epoxy. Okay, so we have a zinc layer, and then on the top of zinc layer we have a epoxy coating. So that's why it is a dual zinc galvanized coated bar. Okay, so all these coatings over the reinforcement surface, they act as a barrier for oxygen, moisture, and chloride ions to interact with the steel surface, so they can significantly delay the corrosion initiation. However, until these coatings are intact, they can offer significant improvement. Okay, but like if the coating has undergone any damage, suppose between these two points there is no coating. Okay, so what will happen, these such type of damage over coating, they can pose a significant risk for corrosion. Like they can cause crevice corrosion or underfilm corrosion or macrocell corrosions. Okay, so due to such severe corrosion conditions, the coated rebar can be worse than normal uncoated rebar also. So that's why use of coated rebar needs utmost care for effective application. A damaged coated rebar is worse than a non-coated rebar. Okay, so protecting these rebars against damage before being used in concreting is very important. Okay. Now, instead of coating over reinforcement, we have special alloyed reinforcement also, like stainless steel and corrosion resistant steel. Okay, so these rebars will, like the in stainless steel, we have higher proportion of chromium in the composition of steel. Okay, and chromium is responsible for making a strong and a stable passive layer. Okay, so what happens when there is higher chromium content in steel, the steel forms a chromium oxide layer over its surface, which is a very strong passive layer, and it doesn't break easily in the action of chloride ions. Okay, similarly in corrosion resistant steel also, there are higher proportion of chromium, nickel, and other elements which forms a stable passive layer over the steel surface. Okay, so these rebar, they make these higher content of chromium and nickel, it makes steel naturally more resistive to corrosion, and it offers a better choice over a coated reinforcement where damage can be an issue. However, it has been found that this CRS bar, okay, there this chromium and nickel content are just good enough so that these bar won't corrode naturally. Okay, in atmosphere, like you will generally see when we just keep a steel reinforcement bar outside in environment, it will start to rust. Okay, before being used for concreting. So CRS bar is just good enough that if they are kept outside in environment, they won't rust. Okay, before being used in concrete. And stainless steel, they are highly effective against corrosion, but it is also very costly. Okay, it is at least 3 to 4 times costlier than normal steel reinforcement. Okay, because of which its use is very limited in commercial application. And finally, we have corrosion inhibitor admixtures. So these are a type of chemical admixture. It can be a liquid or can be a solid, which is added as an admixture during concreting in a very small dosage. So generally, the dosage of corrosion inhibitors are in the range of zero point 0.2 to zero point 0.4 kg per meter cube of concrete. Okay, so in this range they are added as an admixture in concrete. So what happens, these chemicals, what they do, they diffuse through the concrete cover and they form a stable protective film over the steel surface. Okay, they can chemically absorb over the steel surface and form a barrier against oxygen, moisture and chloride attacks. Okay. Okay, so this is the action of corrosion inhibitors. So they absorb over the surface of steel and they form a barrier against oxygen, moisture, and chloride ions. So either they can function in two ways. Either they can form a film over the steel surface, or they can block the pores that are present in the cover concrete. So if they will form a film on the steel surface, they are making a barrier against oxygen and moisture, okay, for interaction with steel. Or if they block the pores of the concrete cover, they will delay the ingress of oxygen, moisture and chlorides through the cover concrete. So either of the two mechanism, they will delay the corrosion initiation. So, among all choices of corrosion control that we have seen, that is using high quality concreting or applying a coating over concrete surface or using coated reinforcement or alloyed reinforcement, the use of corrosion inhibitor is considered the cheapest and the most easiest one. Okay. And although its efficiency is not very high compared to an undamaged coated rebar or alloyed reinforcement, but since it is easy to use, it is often preferred in commercial application. Like up to low or moderate exposure condition, they form a very effective film, okay, against chloride attacks or aggressive ion attacks. However, in very severe exposure condition, like if we talk about a structure which is present very near to the shoreline or in an area where there is high chloride exposure conditions, then in such cases such corrosion inhibitor they may not be effective. Okay. So this was all about different corrosion control methods. Okay. Now based on your understanding about corrosion control methods, just try to answer these questions. And in the meantime, if you have any doubt, you can ask. Okay, so whatever I discussed here, like in the NPTEL course, I guess only role of concrete quality was discussed, but I have added few more extra slides here so that you know all the different corrosion control methods. Okay, for just for your knowledge. So in addition to concrete quality, we discussed about coating over concrete surface. We talked about coating over reinforcement. We talked about alloyed reinforcement, and we have discussed corrosion inhibitors also. So if you have any doubt regarding any of these methods, you can ask. If not, just try to answer question number 4. So question number 4 says, which of the following combination most effectively delays corrosion initiation in a reinforced concrete structure? Anyone knows the answer? What will the answer for question number 4?
Low. Question number 4 answer is C. Low permeability.
Yes, the correct answer is C. So low permeability, low pore connectivity, dense and thick concrete cover. these combination will effectively delay the corrosion initiation, because they will slow down the ionic ingress that will happen to the cover concrete. Okay, and if the ion ingress will be slow, then the corrosion initiation will be delayed. Question number 5. Which of the following interventions primarily act in reducing anodic kinetics rather than delaying initiation? Okay, so there are four methods that have been mentioned here. Okay, which method will reduce the rate of anodic reaction? Okay, that I want to know. So there can be multiple right answers. So we know corrosion is made of two half cell reactions. One is anodic reaction and one is cathodic reaction. So among these four options, which will reduce the rate of anodic reaction? Yes, B is one of the correct option. Any other option that you see is correct? Okay, so we have talked about cathodic protection using zinc. Okay, so zinc act as a sacrificial anode. So zinc will become anode and it will make iron act as a cathode. So it will reduce the rate of anodic reaction. Okay, so instead of iron corrosion, zinc will corrode. So that is one way to reduce the rate of anodic reaction at steel surface. What can be the other way? Okay, C can also be a correct option. Use of corrosion inhibitor. So certain corrosion inhibitors like calcium nitride, if you know, they promote passivation of steel. Okay, so they enhance the passivation tendency of steel. So if steel passivation tendency will increase, so the rate of canodic reaction will reduce. Okay, so that is one way in which corrosion inhibitor can also reduce the rate of anodic reaction. Or if they chemi absorb over the or if the chemical react with the steel surface and they form an additional barrier. Okay, so then that way also they will reduce the anodic reaction rate of steel. Now answer these three questions. So question number 6 is, a structure designed with low permeability concrete shows early signs of corrosion. What is the most plausible cause? Okay, though that concrete was designed for with low permeability, it still showed early corrosion. What can be the reason? Yes, the correct answer is B. Poor compaction leading to interconnected pore. So suppose I have designed a concrete to function as a M55 grade concrete. Okay, so that M55 grade concrete will have a low permeability. It should have a low permeability. However, on site when we were pouring the concrete, the compaction was not proper. Okay, so what will happen, it will have a lot of interconnected pores inside. Though it was designed for low permeability, it has a lot of interconnected pores due to poor compaction. Okay, so due to this, ionic ingress will be easy and it will show early corrosion initiation signs. Okay, so that's why site control of concrete becomes very important for both mechanical properties and for durability properties also. Question number 7. Which option provides long-term reliability against with minimum dependency on workmanship quality? So, like among these four options, which is the best option to increase the durability of a reinforced concrete without much dependence upon the workmanship quality? Any idea for question number 7, which will be the correct option? No, surface coating will depend upon workmanship quality. Suppose you are coating the concrete surface and it is not coated properly, you have left some part uncoated, so that part can become an easy source for ionic ingress. Okay, the correct option will be use of stainless steel reinforcement, because when we talk about stainless steel, they are manufactured in industry. Okay, and they have stainless steel has higher chromium content in its composition. Okay, so such rebar, they don't depend much on the workmanship quality on field, because they have naturally high corrosion resistant tendency. So quality of concrete or amount of inhibitor that is poured on amount of paint that is applied over the coating, over the concrete surface, or over reinforcement, all these things can be affected by workmanship quality, but not stainless steel. Okay, if we have a stainless steel reinforcement properly manufactured in industry, it will have minimum dependency on workmanship quality on field. Question number 8. A coastal bridge shows chloride content exceeding the threshold. Okay, so if you remember in corrosion initiation, we have said that when the chloride content at the steel concrete interface exceeds the threshold value, then corrosion initiate. Okay, so on this coastal bridge, chloride content exceeded that threshold value, but still there was no visible cracking which was visible on the concrete surface. Okay, so which possible combination is most effective to arrest propagation? Okay, so we know corrosion has initiated, but there is no cracking on the surface yet. So if we want to delay the propagation, which combination of techniques we should use? Any idea for question number 8? What can be the correct option? Just think about all the different corrosion control techniques that we have discussed and how they are affecting or how they are delaying corrosion. Now, knowing that corrosion has already initiated, which technique will still work effectively? So stainless steel bar, they are generally used like if we have a good budget in construction. Okay, we know stainless steel bars are really expensive, but suppose we are doing some construction very close to marine exposure, like very close to seashore, where a normal steel bar won't be effective or won't survive for long, then for such cases we may prefer using a stainless steel bar. Okay, though they are expensive, but again it depends upon the budget of construction whether it is possible to use a stainless steel bar or not. Or if we talk about a steel infrastructure where there is no concrete and that steel infrastructure is present in chloride exposure zones, so there they may use stainless steel instead of normal steel for construction. Okay, answer for question number 8 will be B. Okay, so we, since corrosion has already initiated, then so any kind of surface sealer or use of low quality concrete, high quality concrete won't make any sense because corrosion has already initiated. So once corrosion has initiated, our target should be to protect the structure. Okay, and that for that we can use cathodic protection. Okay, so we can use an impressed current cathodic protection technique, which will slow down the anodic reaction rate once we know that corrosion has initiated. So if we slow down the rate of an anodic reaction, we'll slow down the rate of corrosion also, which will effectively delay the propagation. Okay, I hope these questions are clear to everyone. If yes, we'll move to the last part. So this is a little bit additional that I'm talking in this session. Okay, so this is like in situ monitoring of corrosion activities. So this topic is very important if you will look on the future in corrosion science understanding. So you should know when we go on field how we assess corrosion activities. So for that I have prepared 2 3 slides. It will be a quick discussion, like 5 10 minutes discussion, but it will give you complete clarity about corrosion in reinforced concrete, because now we know about corrosion, we know the thermodynamics, the kinetics and corrosion control methods. So it is also important to know monitoring of corrosion activity. Okay, so if we look into different ways in which we can detect corrosion in situ condition, one of the most commonly used technique is the half cell potential measurement. Okay, so this method, what it does, it measures the electrical potential difference between an embedded steel and a reference electrode placed on the concrete surface. So we know corrosion is made of two half cells. There is anodic reaction and there is cathodic reaction. So at steel, Fe is converting into Fe2 plus. That is my anodic reaction half cell. So to complete the circuit, we place a reference electrode on the surface of concrete, which will act as a cathode. And when we connect these two systems together, uh, knowing the potential of cathode, we can calculate the potential of anode. Okay, so that will give us the corrosion potential. Okay, so this reference electrode is a material of whose potential we know. Okay, so knowing the potential of a reference electrode, we calculate the electrode potential for corrosion. So this is the basis of half cell potential testing. Okay, so the fundamental principle, if I will repeat again, is when steel is actively corroding, it act as an anode. Okay, so if it is acting as an anode, it will show negative potential value when it we measure against a reference electrode. Okay, so from this, what we are obtaining, we are obtaining the probability of corrosion, since we are talking about potential. Okay, and we are not obtaining the rate of corrosion. Okay, so if you see, there are different types of half cell reference electrodes that are available. So the one which is shown here in this diagram, this is copper sulfate half cell. Okay, and in this diagram also here. Okay, so we have a copper sulfate reference electrode. Okay, so for we have a table that is given in IS code, which says that whatever reading we get in a voltmeter when we make this half cell connection of steel rebar and copper sulfate, so if this value is less than minus 200 millivolt, less negative than minus 200 millivolt, then we say that the probability of corrosion is very low. Okay, if this value is minus 250 to minus 350 millivolt, then we say that corrosion activity is uncertain. And if this value is more negative than minus 350 millivolt, then we say there is higher probability of corrosion, and above minus 500 there is severe corrosion. Okay, so there this is for copper sulfate reference electrode. Similarly, we can have a HgHgCl2 reference electrode or an AgAgCl reference electrode. So for each reference electrode, this probability marking, likelihood of corrosion marking, it differs. Okay, so for copper sulfate, 350 is the critical potential point. For HgHgCl2, 276 is a critical potential point, and for AgAgCl, 256 is our critical potential point. Okay, so if a potential value is more negative than minus 350 for a copper half cell reference electrode, then we say there is high probability of corrosion. So, if we measure half cell potential valued as at different points on a concrete surface, then we can make a corrosion potential. We can perform a corrosion potential mapping. So here you can see multiple readings are taken over a grid, and we have made a contour plots. Okay, so this helps us to allow identify what is the distribution of corrosion activity, and it helps us to detect localized anodic regions also. So you can see this red spot, it represents that potential here is negative, more negative than minus 350. However, green zone represents their potential is less negative than 350. So such spatial distribution can tell us the probability of localized corrosion that is occurring inside a reinforced concrete system also through corrosion potential mapping. Then second method is concrete sampling. So typically through core extraction. So what we do, we extract a concrete core from a concrete surface, and then from this core we do chloride profiling, carbonation depth modeling, and sometimes microstructural testing also, like porosity and pore connectivity. And such testing can give us an indication of how much ions have how much quantity of ions have went inside, and what is the diffusion coefficient, or what is the carbonation depth. Okay, so such data we can get if we collect concrete samples from various depth. Okay, using coring. Then we have guard ring linear polarization resistance technique. So this is an electrochemical technique which helps us to estimate the corrosion current density. And if we know corrosion current density, we can estimate the corrosion rate also. So the key idea here is that we apply a very small permutation potential. That neta is very close to zero. Okay, so if apply a very small permutation potential, then using Stern-Gary relationship, we can estimate the corrosion current. Okay, so we know R is equal to delta V by delta I. Okay, so if we apply a very small permutation potential and we measure the resistance of the concrete of the steel, then knowing the R value and delta V value, we can calculate the delta I. That is my corrosion current. Okay, so this is the basis of guard ring linear polarization resistance technique. So this ring, it defines the area which is getting polarized. Okay, so for this area we are determining the current density. So again we can do this test on spatial distribution also, so that we can know if there is any localized area where there is higher shoot in current density. So if there is higher shoot in current density locally, then that area might be due to that area might have risk of pitting corrosion inside. And the fourth technique is the measurement of concrete resistivity. Okay, so this in this testing we measure the resistivity of concrete. So we are not dealing with the steel reinforcement, we are dealing with the concrete. We are measuring the resistivity of concrete, and the resistivity of concrete controls the ease of ionic movement. Okay, so if concrete has lower resistivity, then ionic ingress through concrete will be faster. If concrete has higher resistivity, that means that ionic ingress through concrete cover is lower. Okay, so lower resistivity means higher ionic mobility, so higher corrosion risk, and higher resistivity means lower ionic mobility, so lower corrosion rate. Okay, so this is the basis of concrete resistivity technique. So there is 4 probe resistivity meter, and there are 2 probe resistivity meter also, which can help us to measure the surface resistivity of concrete cover. Okay, so these are different types of in situ monitoring testing for corrosion activities. Now based on these techniques, just try to answer these 3 simple questions, and if you have any doubt regarding any of the testing, you can ask. These are very simple questions, you just try to quickly answer this question, Shreyash. So question number 9 is, a 25-year-old marine structure was showing no visible cracks, okay, but corrosion risk is still suspected. So which of the following combination gives the most reliable estimate of early stage diagnosis? So if I know that there is no cracking but still there is risk of corrosion inside, then what testing combination I should use to assess the structure? And I know the structure is located in marine environment. Yes, the correct answer is half cell potential plus chloride mapping. Okay, so since it is located in marine environment, it means that it is prone to exposure to chloride ions. And due to chloride ions, we know there is risk of pitting corrosion or localized corrosion. So that's why there is no visible cracks available on the surface, but risk inside is high. So half cell potential mapping will give us an estimation of localized corrosion inside, and chloride profiling will help us to give an idea of up till how much depth chloride has been penetrated. Question number 10. Why is concrete resistivity testing critical in interpreting corrosion risk? So, in concrete resistivity testing, we are not measuring the resistance of steel rebar or anything, but any potential of steel rebar. But still, why it is critical for predicting corrosion risk? Any idea what can be the correct answer? Yes, the correct answer is B. Okay, so when we talk about resistivity of concrete, concrete which has higher resistivity has higher resistance against ionic mobility also. So we can say that resistivity governs the ionic movement, and ionic movement will in turn govern the risk of corrosion. Question number 11. Half cell potential shows higher probability of corrosion. So suppose in half cell potential mapping we got a, a, a corrosion potential value of minus 400 millivolt with respect to copper sulfate half cell, but resistivity of concrete is high. Okay, so what is the best possible interpretation of such condition? So we have very high negative value of half cell, but we have very high resistivity of concrete also. So what you will interpret from such structure? Any idea? Yes, the correct answer is C. Okay, so corrosion is possible because potential is in the higher probability. Okay, so corrosion is possible, but rate will be low. Why? Because concrete has high resistivity. So the movement of ions through concrete cover or the diffusion of oxygen or moisture through concrete cover, it will be slow. So the rate of cathodic reaction will be slow. So overall rate of corrosion will be slow. Although corrosion is possible, but the rate will be pretty slow because of high resistivity of concrete. Okay, so this is how we can monitor corrosion on site and we can have an estimation of corrosion. Okay, so this was all for today's session. We first had an overview of kinetics of corrosion. We understood Water-Warmer equation, Evans diagram, and corrosion rate calculation. Then we discussed different methods to control corrosion in reinforced concrete by understanding concrete quality, role of coating and reinforcement, and role of use of corrosion inhibitors. And finally, we discussed different techniques used for in situ monitoring of corrosion activity, where we covered half cell potential testing, we talked about concrete core testing, we talked about linear polarization resistance measurement, and we discussed concrete resistivity measurement. Okay, so this was all for the session. Thank you.